Okay. We know we have some network problems, and the objective is to determine the maximum amount of flow that can generated through a network, and the arcs links in these network problems have upper bound and lower bound limits, right? And for example, how much water can flow through a network of pipes in Jersey City, and how many cars can travel through a network of street within a state. When you do transportation planning and facility infrastructure planning, you may use some other kind of network problems. So one of them is a maximal flow problem. Here's an example of pipelines and detailed problem statement. I'm going to skip, but I'm going to redraw the diagram on the whiteboard to explain. So, okay, from oil field 1, so node 1, and refinery 6, right? And you go through pump stations and 2 and 4. So all these arcs are directional, and you can go through pump station 2 and 4, which node 3 and 5, and you also can push oil through 2 to 5 and 3 to 4, 2 to 5 and 3 to 4, and 5, 6 are connected. The thing is, each node may have capacity, or arcs pipeline will have capacity, depend on diameter size. But we just assume from 1 to 2, you only have 6 capacity, and there is upper limit, and lower limit is 0, because you are not going to make it negative flow. From 1 to 3, 4, and 2, 3 to 5, 5, 3 to 4 is 2, and 2 to 5, 2, 2 to 4, 3, and 4 to 6 will be 6, 5 to 6 will be 4. Okay, before using network flow problems, so we can assign traffic flow as much as we can, right? And the way to do that is select either route. So let's select 1 through 5, 6, right? Through 1, 3, 5, 6, what is the minimum capacity of this path? Four, 5, 4. So if 4 is the minimum out of 4, 5, 4, we can assign 4 to this arc, and then 4 here, and then 4 here. We have extra 1 capacity. Then let's select this route. So what is the minimum out of 6, 3, 6? 3. So we can assign 3, 3, and 3. This is already full capacity, so you cannot assign anymore. But let's choose the other route. This is full, so we can select what? Which way? There's no way, right? So we have we 7 outflow and then 7 inflow, so maximum flow is 7. But you sure this is the right answer? We are not sure yet. So we're going to use different way to solve this problem. Okay, for this kind of maximal problem, we have origin, which is oil field, and destination, which is a refinery. So let's say we have a maximum inflow to node 6, then it goes back to node 1. This is a dummy link, dummy artificial link. Then it should be 7 goes to node 1. But actually it doesn't go, but we just assume it goes back to node 1. So what are the decision variables for this problem? So you can assign as much as you can from node 1 to 2. So let's say flow 1 to 2, let's say x12 and x13, x24, x25, x34, x35, x56, x46. So number of arcs are the number of decision variables. So actually we have another dummy artificial link, which is x61. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 decision variables. 1, 2, 3, 4, 5, 6, 7, 8, 9. So x61 is dummy link. Good. The question is, what is objective function? So this is a maximal problem. We try to maximize total flow through this network from 1 to 6. 1 to 6. Then we assume all inflow to node 6 will go back to node 1. So these dummy artificial link will be maximized. So our maximum will maximize x61. If we maximize this dummy artificial link, we can maximize total flow from 1 to 6. Did you get what I'm saying so far?
Yeah, Professor, we hear you.
All right, thank you.
You're welcome.
I want to make sure you're there. Now, this object function is subject to several constraints. Now, something different from previous problems. We have inflow and outflow, inflow, outflow. If you have a supply node, that will have negative numbers. And if you have a demand node, that will be positive numbers. But in this case, we have a backward loop kind of, which is a dummy link from 6.1. So actually, there's inflow is equal to outflow. So all nodes will have the same A. So we don't have supply and demand. So all nodes will have demand 0. So let's figure out the constraint from node 1. Okay, node 1 constraint. So inflow should be equal to outflow. which is inflow equal to outflow, right? And then we have a capacity of the arc, right? So I have arc capacity, say lower bound and upper bound. Are there a couple of ways to say in math? So we say these variables should be greater than equal to 0, and then we just have upper bound, and we can say each arc would be greater than 0 and less than equal to upper bound, because you have lower bound and upper bound over each arc. Now let's say from node 1. Node 1 inflow minus x61, right? x61 should be equal to x12 plus x13. Right? If you move all variables to the left hand side, equal 0. So and node 2, there is only one inflow, x12 equal to outflow x24 plus x25, which is equal to x12 minus x24 minus x25 equal to 0. And the node 3, there's only one inflow and then two outflows. So one inflow x13 minus x34 minus x35 equal to 0. Now, node 4, constraint node 4, we have two inflow and one outflow. x24 plus x34 minus outflow x46. And node 5's constraint, we have two inflows from 3 and 2 and one outflow. So x25 plus x35 minus x56 equals 0. Node 6, we have two inflows and one outflow. x46 plus x56 minus x61 equals 0. Now we have arc capacity. So arc x12, so that means x12 should be greater than equal to 0 or less than equal to 6. You can also assign more than 6 onto arc x12. But anyway, to make it simple, let's say all these variables should be greater than equal to 0, right? Then we just write upper bound. So x13 should be less than equal to 4. Then x24 should be less than equal to 3. x25 less than equal to 2. x34 less than equal to 2. x35 less than equal to 5. x46 less than equal to 6. x54 less than equal to 6. Right? Then x61 unlimited. So we can say actually x16 or very large number 99999. Well, we can just use this symbol. Okay, this is about maximal problem. And equations.